There is a mistaken belief that since every factory car is tuned to aggressively target a stoichiometric AFR at idle and cruise, that this is where we'll see optimal fuel economy from an engine. As we've just seen, this AFR is chosen due to emissions purposes, but it also happens that it does do a pretty good job of offering good fuel economy too. If we don't need to worry about emissions compliance, we will actually see a small but measurable gain in fuel economy by running the engine slightly leaner than stoichiometric. There is a limit to how far we can go though, since as we lean the mixture out, the engine torque output will also reduce. This means that we'll need to increase our throttle opening to maintain a constant speed on the road, and hence this can counteract any fuel savings. In practice, we find that the best fuel economy is achieved with an AFR between 1.03 and 1.05 lambda. We've talked about how air-fuel ratio can affect the economy of our engine, and I'm going to perform a quick demonstration now on the dyno that I hope will illustrate that point. I do want to just mention that it is a tricky demonstration to perform because the sort of changes we're looking at in injection pulse width as we vary the air-fuel ratio are quite small, but hopefully this will still illustrate the point. Now, one of the key aspects with this test is during the test, as I vary the air-fuel ratio from rich to lean, I'm going to need to make sure that the amount of torque the engine is producing stays consistent, otherwise the test isn't that relevant. The reason for that is when we're cruising at a constant speed on the open road, we need a certain amount of torque from the engine in order to maintain that speed. So what we're looking at is minimizing the fuel consumption at a given RPM and engine torque. And we're going to be measuring that fuel consumption for this particular test by way of the injector pulse width. So we're using for this test an AEM Infinity ECU, and let's just have a quick look at the Infinity software so you know what I'm going to be doing for this particular test. Here we have our lambda or air fuel ratio target. So this is the target air fuel ratio or lambda values we want the engine to be running. We have load and manifold pressure on our vertical axis, and on our horizontal axis here we have our engine RPM. We've got a graphical representation of that table across here on the right so we can see the general shape and trend of the table. Now on the left hand side we've got some important data to look at. We have first of all our lambda 1, which is the air fuel ratio being measured in the exhaust by a wideband oxygen sensor, and below that we have the lambda target, which simply comes straight from our lambda target table. Above you'll be able to see we have our throttle position, our engine speed and our manifold pressure. The point that we're going to be looking at, the key parameter that we're going to be looking at, is our injection 1 pulse width. Now, this is the pulse width in milliseconds being sent to the fuel injectors. In this case we're simply monitoring injector 1, but all of the injectors fitted to the engine are receiving the same injector pulse width. That value is being shown here, so this is what we're going to want to monitor. We've also got the data being shown below in our data log, and we've got our lambda 1 value, our target lambda value, our injection pulse width, as well as our throttle position. So what I'm going to do is just get the engine running now on our dyno, and for this test I'm going to be running the engine at around about 2000 RPM, and what I'm going to do is get the engine running to a point where it's generating around about 100 Newton meters of torque. So let's just jump across to our dyno now, and what you're going to want to be watching during this test is our torque graph. Now this will update in real time as the engine torque changes. We can see it graphically being shown, as well as we have an actual torque value in Newton meters shown at the bottom here. So my challenge during this test is going to be to maintain as close as I can to 100 Newton meters of torque, and that is actually quite a lot harder than it might sound. So let's start in our Infinity software now by just highlighting the entire range of cells that we're operating in, and I'm going to start by targeting 0.95 lambda. So this is a little bit richer than we would typically run at cruise, but I want to illustrate how that air-fuel ratio affects our injection pulse width. So what I'll do is I'll just drop the throttle very slightly. We'll get ourselves down to 100 Newton meters of torque, and as soon as we do that, we'll have a look at our injection pulse width. And at the moment we're sitting at 100 Newton meters, and we have about a 2.40, 2.39 Newton meter, millisecond pulse width being sent to the injectors. So that's our baseline, 2.40 milliseconds. Let's just lean the air-fuel ratio off now to lambda 1, and we'll get back to 100 Newton meters now. And you can see that at 100 Newton meters, again, obviously our torque is varying a little bit. At 100 Newton meters, we're now dropped to 2.35, 2.37 milliseconds pulse width. So we've gone from 2.40 at lambda 0.95. We've gone to lambda 1 now, and our millisecond pulse width has dropped to about 2.36. So you can see we've seen a small reduction in the injection pulse width, which corresponds to a small reduction in the amount of fuel being used. Let's now lean our air-fuel ratio off further to lambda 1.05, and we'll get our torque back to 100 Newton meters. And at 100 Newton meters now, no, we're just oscillating around. Okay, so we're sitting now at about 2.34 to 2.35 millisecond pulse width being sent to the injectors. So we've dropped from 2.36 down to 2.35. So we've seen a small improvement. It's not a very large improvement, but we have seen another improvement. Let's now target lambda 1.1. So we're now going leaner again. We'll do that, and now the torque has dropped off with the same throttle position, and this is natural. This is because we're going leaner and the torque production of the engine has reduced. I'll get back to 100 Newton meters, and as soon as we do that, we can see that our injection pulse width is still the same, sitting at about 2.34, 2.35, 2.36 milliseconds. So going from lambda 1.05 to 1.1, we haven't seen any improvement, any reduction in our injector pulse width. So leaning the air-fuel ratio out there hasn't actually seen an improvement in economy, because when we leaned out the air-fuel ratio, the torque dropped, so I had to open the throttle further to get the torque back where we wanted it, back to that 100 Newton meters, and that of course uses more fuel. Let's do one more test. Let's go to 1.15 lambda. So this is generally much leaner than we would run. Again, we see the torque drop off, and I need to open the throttle in order to get back to our 100 Newton meter torque target. And now we can see we've actually increased our injection pulse width. We've gone up to about 2.35, 2.36. So we're starting to see the economy drop off as we move leaner. So hopefully this just goes some way to illustrating what we've been talking about in the course, where there is a trade-off between our lambda target and our fuel economy. As we lean off the air-fuel ratio, we lean off our lambda target, we see the fuel economy improve, it'll plateau, and then it will drop off because the engine's physically not making enough torque. The torque is reducing, so in order to keep the car rolling at a constant speed on the open road, we need to therefore open the throttle, and that's going to result in more air and fuel being combusted, which becomes a negative effect on our fuel economy.